Rorabaugh from USC Columbia. He's going to talk about Collat's generalized, an expansion of the 3x plus 1 problem, maybe one of the most beautiful problems in mathematics, I would say. Still unsolved after how many years? Maybe 7?
Yeah, it's pretty old.
Okay, so Danny?
Hello, I'm Danny Rorabaugh. I'm a second-year graduate student in mathematics, pure mathematics at University of South Carolina. What I'm presenting to you today is my senior research as an undergraduate at Seattle Pacific University under Dr. Robin O'Leary. This is Collat's generalized, an expansion of the 3x plus 1 problem. Now, throughout this presentation, I will be telling you what the problem is, of course. It's called the Collat's conjecture. I'm going to be going through a few key terms and details, such as trajectories and Collat's trees. And then I'm going to tell you about what I did specifically, the generalization of the problem. And then hopefully I can give you some results from my research in terms of some basic categories and in a manner that you will be able to appreciate. So let's get started. The Collat's problem. This is an unsolved number theory problem based around what's called the 3x plus 1 function. It's a piecewise function defined on the positive integers. Function c, if it has an odd input, you multiply it by 3 and add 1. And if the input is even, divide by 2. So, not too bad of a function. And the conjecture that Lothar Collat's made some decades ago, over 50 years ago, was that if you start with any positive integer, no matter what positive integer you pick, and you repeatedly apply this function, take the output of the function, put it right back into the function, you will eventually reach the number 1, no matter where you start. So, this is a conjecture. People have used computers to verify that this is the case for all positive integers up to 10 to the 18. But it's still just a conjecture. It hasn't been proved for everything. So it's been a fun conjecture for a lot of number theorists since it arrived. Now, one of the first key terms in discussing this will be trajectories. Whoa, what in the world? Oh, I hit end. There's an end button here. Woohoo! That's scary. Trajectories. So we define the trajectory of a number x as the infinite sequence of successive iterations of the c function, beginning with x. X, c of x, c of c of x, c of c of c of x, etc. And using this definition, we can restate the conjecture as follows. The trajectory of every positive integer contains 1. So 1 shows up somewhere in the sequence, no matter what x is. Just a restatement in slightly more or rigorous terms or alternate terminology. A few related definitions. We say that a trajectory converges if any of the elements repeat. So if an element shows up and then shows up again later, that's convergence. And when that happens, the numbers that it hits will start looping. And so we'll call the ordered set of repeating elements a loop. And otherwise, if this doesn't happen, we say it diverges. This is different from series and sequence divergence and convergence that you'll see in calculus. So try to put those out of your mind for the moment. As an example, if we start with 5, and we create the trajectory of 5, 5 multiplied by 3 and added 1, and with 1 added gives us 16. That's even. We divide by 2 and get 8. That is even. We divide by 2 and get 4. And that's even. We divide by 2 and get 2. Once again, we divide by 2 and we get 1. Now, if we want, even though we've already reached 1, we can put 1 back into the function, multiply by 3, add 1, and we get 4 again. And so 4, 2, 1, 4, 2, 1 will repeat over and over, and we'll call that loop, that repeated part of the series, of the sequence, a loop. Okay, so there's trajectories. The other main way we'll look at this problem is with what's called a Collatz tree. And so here is, well, it's created using the inverse mapping C inverse. So if we start at 1, we see what numbers go to 1 when put in the C function. 2 is the only option. We see what numbers go to 2. 4 is the only option. What numbers go to 4? 1 and 8. So, and what numbers go to 16? 5 and 32 both go to 16. So we'll branch out by doing the inverse mapping, and it grows quite a bit. I do want to apologize to any graph theorists. This isn't a tree, but it's called the Collatz tree. So, anyway. What we can do with this new perspective, rather than trajectories, we can restate the conjecture one more time in terms of the tree in the following manner. The Collatz tree, with all of the positive integers, is connected. So the idea here is no matter what integer you get, it will land somewhere in the tree, it will connect down back to 1, instead of needing a separate little tree growing off somewhere else from a different number. So that's just another way to look at the conjecture. So, some things to consider, some little details when working on this project. Why are we only working with positive integers? Why not 0? Why not negative integers? And the answer may be pretty obvious if I show you the trees, if we work with all integers. It seems that everything's connected with the positive integers, but 0, under the C function, loops to itself, and we have at least 2 distinct sections to the negative integers in this regard. So it's not as beautiful as a result, it's not as interesting of a result when you're working with, when you allow for 0 and negative integers. So that's why we stick to positive integers. It disconnects the tree if we don't. So, what did I do with the problem? The 3x plus 1 problem has been attacked by many people, many mathematicians far more experienced than I am. So what could I, as an undergraduate 2 years ago, do with this problem? Well, generalizing. That's a method you can always use if you're not sure what to do with the problem. You can generalize it and see if there's something on a bigger scale that you can notice. So I generalized the C function in the following manner, as an ax plus b function. If the integer you're putting in is odd, multiply by a and add b, instead of multiplying by 3 and adding 1. Just a different variation that has more possibilities than the original problem. And for more really minuscule details that I worked out in my paper, it's better if you let a and b be odd. It's kind of silly to let either of them be even, it just doesn't work as well. For similar reasons to why we rejected negative integers. So, as I said, the generalization is to back up and try to get a different perspective on the problem. So, backing up and allowing for a different function to act on the odd numbers might give an idea of why 3x plus 1 works so well, or at least appears to work so well. Again, it's just a conjecture. And in order to work with it more efficiently, we create some variations of the C function, and you'll see these variations in other people's work on the problem as well. So we have the original function, the C function, but if you think about it, if A is odd and B is odd, and you take an odd integer and you put it into your C function, an odd integer times an odd integer plus an odd integer is even. So you're always going to get an even output to an odd input. So you might as well just divide by 2 automatically. Save some iterations, speed up the process a little bit. So this is another function that does kind of the same process, it just does it faster. We can take that idea to an extreme, and we can create what's often sometimes seen as the T function, and just divide by the highest power of 2 possible, and ignore even numbers altogether. Really, it's what's happening with the odd numbers that runs the whole show. So here, ax plus b, you divide out by the highest power of 2 you can, and you go back to an odd number. So, what were my goals in doing this? I wanted to see which values of a and b would satisfy my 2 variations of the Collatz conjecture. So which values of a and b cause every trajectory to contain 1? Or maybe which values of A and B cause us to have a connected Collatz tree. And these aren't the same thing. Different values of A and B will have one result and not the other. So sometimes it's important, even though these are the same thing in the original problem, to let them be different things within the generalization. And I'll break it into 3 categories that computationally will pair up pretty well. A less than, equal to, and greater than 3. Let's go through those. If A is less than 3, odd positive integers, we're only dealing with one option. We can look at what happens to x if x is greater than b. If x is greater than b, consider using the d function, then x plus b over 2, well, x is greater than b, so that's strictly less than x plus x over 2, which is equal to x. Or if x is even, we divide by 2, and that's less than x. So what we see is when x is greater than b, in this case, the d function is decreasing, or it's causing a decreasing sequence. So that's pretty well contained. What if x is equal to b? Well, if x is equal to b, then d of x is equal to b. You're stuck. And if x is less than b, then we find that from the same type of calculation, d of x is still strictly less than b. So it's a fairly well contained situation. And that first line, the fact that numbers larger than b will iterate to smaller things, tells us that every trajectory converges. We're getting everything eventually down to something less than or equal to b. And then the second and third statement, since this section stays strictly less than b, and when x is equal to b, it iterates back to b, tells us that the tree is disconnected if b isn't equal to 1. So let's see what that looks like. If we're working with a equals 1, b equals 1, the tree is nice, everything goes down to 1 because everything else is greater than 1. But if we allow for, say, b equals 5, we have 2 distinct parts to the tree. One part contains the numbers 1 through 4, and the other contains 5. And there's no way to connect those. It just doesn't work as well when b is greater than 1. You're guaranteed to have a disconnect. So that wraps up that case completely. So then what about a equals 3? I can't tell you everything about this because the original question is contained in here. If I could have that solved, I would probably already have my PhD. Now, one thing we can note, that the following is a sufficient condition. So, if it's true, if the following is true, then we know that every trajectory contains 1. The statement being, for all positive integers greater than 1, there exists a smaller integer in its trajectory. So if every number eventually maps to a smaller number, then, well, that means everything goes down to 1. That's very nice. If we could show that, we'd be done. We can't. But there are some strong statements that are just a little bit weaker that have been proved. Back in the 70s, Terras proved something for the original 3x plus 1 problem. He proved that the values of x, such that x eventually iterates to a smaller number, has density 1 in the positive integers. Another way to say that is 100% of positive integers eventually iterate to a smaller integer. But you got to be careful because 100% of an infinite set is not necessarily all of them. It is a proportional thing. And so not just because this is true, this doesn't mean that every number eventually goes to a smaller number. So it's not quite enough. But it's good evidence that the trend is for everything to, all the trajectory is to decrease as we want. And I looked at his proof through the details and found that it works for all b values. If a equals 3, no matter what b is, then a proportion of 1 of the positive integers will decrease eventually in their trajectory. Again, just good evidence. This isn't proof yet, and proof doesn't exist. Another thing to look at, so that's trajectories, is what about the Collatz tree when a equals 3? Wait, no, we're still on the trajectory question. So, we know that the trajectories decrease, but is it possible for every trajectory to contain 1 for other values of b? So, let's take some x that's a multiple of b. Then what happens? If we look at the c function, well, 3 times a multiple of b plus b is still a multiple of b, so b divides the output of the c function if it divides the input. And that means that b divides everything in the trajectory. That's a problem if b is not equal to 1. So we have to have b equal to 1 for 1 to eventually be in the trajectory of every single positive integer. So no, having other values of b is not good enough. But what's the other question we were looking at? The Collatz tree. And so is it possible for the tree to be connected for other values? Just because 1 isn't in all the trajectories doesn't mean that the tree isn't connected. Let's look, for example, at the case when b is equal to 3. This tree, we start building up from some smaller numbers, appears to be connected, and using Maple, I found that it is connected for all x less than 10 to the 8th. So there's a substantial, there's some evidence there that the tree is connected even when b is not equal to 1. The only thing is, if you consider our last question, 1 is not in the loop. 1 is out here on its own branch. It's not in the main loop. So 1's not there, but it's still possible for the tree to be connected, which is kind of cool. But it's not quite what we wanted. It's not quite as good as b equals 1. Finally, we want to think about what happens if we have a larger value for a. This time we're working with the t function. If you think about the odd positive integers, for every other odd integer, when you submit it to ax plus b, it will be divisible by 2 but not by 4. And if you look at every fourth odd positive integer, it will be divisible by 4 but not by 8. And some fairly simple calculations show that this is the case. If this continues, the 8th positive odd integer, every 8th odd positive integer is divisible by 8 but not by 16. Well, if we look at the probabilities, then we're saying that the probability that our t function, the one that divides out by the highest power of 2, is equal to 2 to the negative k times ax plus b. Well, the probability that that's the case is in fact 2 to the negative k, just looking at the progression of positive integers. Using that probability, we can kind of treat the trajectories like some random process. If we don't know where it started, we just know that the distribution of the odds and the divisibility of ax plus b when x is odd by powers of 2. We know this distribution, so we can treat it like some random process and look at the expected value from x to t of x. So let's look at the expected value of that ratio, t of x over x. Well, an expected value is the sum of the product of all the possibilities times their probability. So we have the possibility of t of x being equal to this times the probability that it's equal to that. We add this up for all values of k. And when we do that, we see we have something that's strictly greater than a geometric series with initial value a over 4 and a common ratio of 1/4. Now the series adds up to a over 3. Remember again, we're in the category that a is greater than 3. So what we're saying is that in general, when we randomly pick a number out of the positive integers, when we randomly pick an odd number, and we look at the ratio of t of x over x, then it's going to be greater than 1, greater than a over 3. So things are tending to move up, even with this t of x function that divides out the largest power of 2 possible. It's of the 3 functions, the one that moves down the fastest. It still tends to move up. So this isn't definitive, but it's still really good idea of the trend going on here to show that the trajectories probably diverge in some cases. Now, when I say this isn't definitive, let's look at an example. Under a equals 5, b equals 1, if we look at the trajectory of 7, we get 7, 9, 23. Again, this is the trajectory under the t function, so no evens. I plotted out the first 300 iterations of this, and we can see the values are growing fairly exponentially. I have a logarithmic scale here, an exponential scale. So it's growing, and it looks like it's not going to stop. But at the same time, if it ever gets to a power of 2, it goes down to 1. It just ends right there. And what's to say it won't do that eventually? I can't tell just because of this trend. So even though this is the general trend of what's going on, we still don't know if it could converge. So the question is just as hard looking at larger values of A. But it just doesn't seem like it's possible. So, in summa, what makes A equals 3, B equals 1 special? Well, for A less than 3, we only had one value of B that was interesting, B equals 1, and it was so trivial that I didn't have to be a college student to figure it out. And neither variation of the Collatz conjecture is satisfied if B is not equal to 1. So, kind of a silly category, nothing's too special about it. If A is greater than 3, although I couldn't really prove anything when I was working on it, I found some good reasons, not just this, there's more in my paper, of why there are problems. Specifically, as I showed you here, the expected value of the ratio of the t of x over x is bigger than 1. So it shows that trajectories tend to grow a lot. And then if we look at A equals 3, even though B equals 3 was nice, it satisfied one of the variations of the Collatz conjecture, it didn't satisfy the other. But in general, for all of the B values, the trajectories do appear to converge, which means that the 3x plus 1 may not be too special, but having the B value equal to 1 does allow for 1 to be in every trajectory, and that's kind of nice as well. But it's a fun problem. It's one of those problems that you can just play with for hours, and sometimes feel like you're making tons of progress, and sometimes feel like you're getting nowhere. And in the end, it was a good way for me to play around with number theory and try my hand at being a mathematician, and I found a few little things, and it was good stuff. Here's my sources. Any questions?
Well, let's thank our speaker.